In this presentation, we will be talking about Graham's law of effusion. Later in the presentation, we will be talking about Dalton's law of partial pressure. So let's go ahead and start out with a brief introduction. According to kinetic molecular theory, which is KMT, there are no significant forces of attraction between gas particles. However, gas particles can flow easily past one another. Often the space into which a gas flows is already occupied by another gas. The random motion of a gas causes the gases to mix until they are evenly distributed. So let's talk about our first term, which is diffusion. Diffusion is the term used to describe the movement of one material through another. For example, air freshener spreading throughout a room. When you first spray the air freshener, it is in a high concentration around you. Slowly, it will fill up the rest of the room. Another example is the aroma of baked cookies. In the kitchen, the aroma is very concentrated. Slowly but surely, that aroma will fill out the entire house. Diffusion is also described as the movement of particles from a high concentration to a low concentration. The second term on here is effusion, and it's a process related to diffusion, except for in effusion, we're talking about gas escaping through a tiny opening. Then it asks, what happens when you puncture a container, such as a balloon or a tire? So think about that for a second. Your first thought is probably like, yeah, they explode. But why? The gas concentration that's inside the tire or the balloon is going to rush out of the tiny hole, which could cause that hole to expand or rip, causing the tire or the balloon to explode. So take a look at the diagrams below. The one on the left represents diffusion, where you can see the particles will slowly mix from high concentrations to low concentrations. The diagram on the right shows effusion, where the gas is going to try to escape through a tiny pinhole opening. So let's talk a little bit about Graham's law. Thomas Graham designed an experiment so that gas is effused into a vacuum. He discovered an inverse relationship between effusion rates. That's the speed and the molar mass. Basically, as the mass of a gas increases, the speed will decrease. Graham's law also applies to the rates of diffusion. Assuming the temperature of the two gases is the same, the heavier particle will diffuse slower than the lighter particle. And that's an important concept you need to know for Graham's law. When using Graham's law, you can set up the proportion to compare the different diffusion rates for the two gases. The equation is as follows. The rate of A over the rate of B equals the square root of the molar mass of B over the molar mass of A. For simplicity purposes, let's make the heavier gas the molar mass of B. This way, whenever you do these equations, you should end up with a rate of a whole number. So let's look at a couple of examples. Example 1, it says compare the rates of effusion of H2 and O2 at the same temperature and pressure. Calculate the ratio of the diffusion rates. So starting on the far left, you can see that I went ahead and I called A H2 and B O2. The reason why I did this is because O2 is the heavier gas. And remember, we said that we were going to call B the heavier gas. Now, looking back at our equation, we have the rate of A over the rate of B equals the square root of the molar mass of B over the molar mass of A. Now, because we don't really have a set speed for A or B, we're going to go ahead and set that equal to 1. So, when we do that, we'll take the square root of 32, which is the molar mass of oxygen gas, over the molar mass of hydrogen gas, which is 2.02. When you do that, you get a rate of H2 that is about 4 times faster. This means that H2 will diffuse about 4 times faster than O2. Example number 2. Calculate the ratio of effusion rates for N2 and N8. So looking at these, once we write down their molar masses, we see that N2 is a heavier gas than Ne. So, again, we'll take these numbers and we'll plug them into our equation. When I do that, I took the square root of 28, which is the molar mass of the nitrogen gas, over the molar mass of neon, which is 20.18. When I did this, I found that neon would diffuse 1.18 times faster than the nitrogen gas. So let's take a look at one more example. In this example, you'll notice that this time we have a speed. So it says, if a molecule of neon gas travels at an average of 400 meters per second at a given temperature, estimate the average speed of the molecule of butane gas at the same temperature. So first, let's write down what we know. We know that neon's molar mass is 20.18, and we can calculate the molar mass of butane to be roughly about 58 grams. Notice that the molar mass of butane is much larger than that of neon, so we will call the mass of butane rate B. It tells you that the neon is traveling at an average of 400 meters per second, so we know the rate of A is 400 meters per second. Now that we have all our numbers, except for the rate of B, we can go ahead and plug into our equation. When we do that, we have 400 over the rate of B equals the square root of 58 over 20.18. Remember, the 58 comes from the molar mass of butane, and the 20.18 is the molar mass of neon. When we solve this out, we end up coming up with a rate for butane of 235.94 meters per second. So take a few seconds, make sure you plug these numbers into your calculator, and you're able to come up with the same answer as I did. Next, we're going to talk about Dalton's law of partial pressure and how it relates to the combined gas law. So a little bit of introduction about Dalton's law. It says, as discussed previously, the space into which a gas flows is often occupied by another gas. As a result, the gases in the space form a mixture, with each gas in the mixture exerting pressure independently of the other gases. So Dalton's law of partial pressure states that the total pressure of a mixture of a gas is equal to the sum of all the pressures of the gas in the mixture. The pressure of a single gas in a mixture is called the partial pressure of the gas. And you can see the equation here. We have the P total equals the P of gas 1 plus the P of gas 2 plus the P of gas 3, etc. Just depending on how many different types of gases there are. P total is the total pressure of the mixture, and P of gas 1, 2, and 3 are the partial pressures of the components. The partial pressure of a gas depends on the number of moles of a gas, the size of the container, and the temperature of the mixture. It does not depend on the identity of the gas. Remember, at the same temperature, the partial pressure of 1 mole of any gas is the same. So let's go ahead and take a look at a couple of examples here. Example number 1 says, find the total pressure of a mixture that contains 3 gases with the following partial pressures: 6.6 kPa, 3.2 kPa, and 1.2 kPa. Remember that the equation for this is the total pressure equals the partial pressure of gas 1 plus the partial pressure of gas 2 plus the partial pressure of gas 3. Because all 3 of these pressures are in the same unit, which is kPa, you can simply add them together. When you do that, you should get a total pressure of 11.0 kPa. Example number 2. A mixture of oxygen, dinitrogen monoxide, and argon has a total pressure of 0.98 atm. What is the partial pressure of dinitrogen monoxide if the partial pressure of oxygen is 0.48 atm and the partial pressure of argon is 0.15 atm? So using the same equation, we have total pressure equals partial pressure of gas 1 plus the partial pressure of gas 2 plus the partial pressure of gas 3. In this case, you are given a total pressure and you are looking for one of the partial pressures of the gas. So you should have your equation set up like I do in the middle. From there, you need to go ahead and solve for this problem, and you should get a partial pressure of the dinitrogen monoxide of 0.35 atm. While collecting partial pressures, there is also something called gas collected by water displacement. Gases often produced in the laboratory are often collected over water. A gas collected by water displacement is not pure, but is always mixed with water vapor. Therefore, your equation would be your total pressure equals the pressure of the gas plus the pressure of the water. You can look at the diagram above, and you notice that they are heating a small amount of substance. When they do that, it will release a gas. That gas will flow through the tube and be collected under water. The gas that is collected under water is also mixed with water vapor, so therefore it needs to be subtracted out. The total pressure when a gas is collected over water can be referenced as atmospheric pressure or barometric pressure. To find the pressure of a gas collected over water, subtract the water vapor pressure at a given temperature from the total pressure. The water pressure varies with the temperature. You need to look up the value of the P of water at a given temperature of the experiment from the table that is provided on the next slide. So this table represents the water vapor at various pressures. Notice that your temperature is in degrees Celsius. You have two types of pressure. Your pressure can either be in mmHg, which is millimeters of mercury, or kilopascal. You have to pay attention to your unit to make sure that everything is set up accordingly. So let's look at a couple of examples of this. Example number 1 says some hydrogen gas is collected over water at 20 degrees Celsius. The level of the water inside and outside the gas collection bottle are the same. The partial pressure of hydrogen is 742.5 torr. What is the barometric pressure or total pressure at the time the gas is collected? Now in this problem, it tells you that you have a partial pressure of the hydrogen of 742.5 torr. In the chart, you can look up the pressure of the water at 20 degrees Celsius. So you may have to pause and reference back to the table to make sure you can find that exact amount. Now remember, in the chart, it gives your pressure in millimeters of mercury and or kPa. Because torr is a 1-to-1 ratio with millimeters of mercury, you can go ahead and use that column. When you look back, you see that at 20 degrees Celsius, your partial pressure of the water is 17.5 mmHg, which will convert to 17.5 torr. You simply plug in that number into your equation and you add them up. When you do so, you should get a total pressure of 760 torr. Example number 2. Helium is collected over water at 25 degrees Celsius. What is the partial pressure of helium gas given that the barometric pressure is 750 millimeters of mercury? In this equation, it is giving you a barometric pressure. Remember that barometric pressure is the same thing as total pressure. It is not giving you your partial pressure of the helium gas. The only other thing that you have is that the gas is collected over water at 25 degrees Celsius. So again, you need to reference back to the chart, look at 25 degrees Celsius, and see what the partial pressure of the water is at 25 degrees Celsius. When you do so, you see that at 25 degrees Celsius, the partial pressure of water is 23.8 mmHg. So go ahead and plug these numbers into your equation, like I have done, and simply solve for the partial pressure of the gas. When you do so, you should get the partial pressure of the gas to be 726.2 millimeters of mercury. Please make sure you go back and always check and make sure my math is correct, and make sure you're able to plug this into your calculator. Gas collected by water displacement continued. So it says, along with finding the pressure of a gas collected over water, you may be asked to find the volume of the gas at a given collected temperature. To perform this calculation, you must do the following. Number 1, find the pressure of a gas at a given collection temperature, just as we did above. Number 2, use the combined gas law to solve for the volume. So now we are taking this one step further, and we're going to be able to use the combined gas law to solve these equations. So for example, it says a sample of oxygen is collected in a 175 milliliter container over water at 15 degrees Celsius, and the barometer reads 752.0 torr. What volume would the dry gas occupy at 770 torr and 15 degrees Celsius? So first, let's go ahead and plug in a little chart on the left, the information that we have in the problem. First of all, it tells us that a sample of oxygen is collected in a 175 milliliter container. Remember when we did these problems from previous that you need to go ahead and convert your volume into liters. So 175 milliliters is going to convert to 0.175 liters. It tells you that it's collected over water and that the barometric pressure is 750 torr. Remember, barometric pressure represents the total pressure, not the partial pressure. So what you'll have to do for this in P1 is right there in the blue box. So it gives you a total pressure of 752. You need to look at the chart and find what the partial pressure of the water is at 15 degrees Celsius. When you do so, you come up with 12.8. You then need to go ahead and subtract out the number, and you come up with a partial pressure of the gas, which is 739.2. The 739.2 represents the P1. Remember, this will be in torr. The temperature of 1 is 15 degrees Celsius. Remember, that temperature does need to be converted into Kelvin. So you add 273 plus 15, and you should get 288 Kelvin. For the partial pressure of number 2, it tells you that the dry gas occupies 770 torr. So that's your pressure of the second one. And at 15 degrees Celsius. So remember, 15 plus 273 equals 288. The only information that it does not give you is the volume of number 2. From here, we can go ahead and remember our combined gas law, which is stated there for you, and go ahead and plug in our numbers. After you plug in your numbers, you see that B2 is the only one without a number tied to it. So we need to go ahead and solve this. When you solve this, you should get a volume of 0.168 liters. Now I'll give you a second to go back, double check, and make sure you can get the same answer. Using moles to find partial pressure. Sometimes partial pressure, which is the P of the gas, can be found using the number of moles. To do this, use the following equation. The partial pressure of the gas equals the number of moles divided by the total number of moles in the problem. Multiply that by the total pressure. So, for example, it says a mixture of 6 moles of He, 3 moles of H2, 4 moles of NH3, 2 moles of CO2, and 9 moles of N2 exert a total pressure of 950 millimeters of mercury. What is the partial pressure of each gas? So from here, you can see that we use that equation. The partial pressure of a gas equals the moles of the gas divided by the total number of moles multiplied by the total pressure. The total number of moles when I added all these numbers together was 24 moles. So, for example, if we do the partial pressure of helium, we see that in the problem it stated that it had 6 moles. So I took 6 moles, I divided that by 24, and I multiplied it by 950 millimeters of mercury. When I did that, I came out, as I follow along to the right, of a partial pressure of the helium of 237.5 millimeters of mercury. Now you'll do the same for each one of these gases to make sure you can solve for it. So take a minute, look through my equations, make sure everything is set up, and try to solve on your own, making sure you get the same numbers that I did. That concludes our PowerPoint over Graham's law and Dalton's law of partial pressure. Please, if you have any questions, feel free to make a discussion post or message me directly.